This is the continued commentary for acetal, ketal, and carbohydrates. Now we're going to focus on molecules with more than one chirocarbon. And it could be 2 or 3 chirocarbons. Two or 3 chirocarbons. And we will try to determine whether the molecule is either going to be a D or L enantiomer. So, first off, let's go ahead and make a very crude distinction between the organic versus biochem molecules. I could give you a Fischer projection like this, in which case you have a chlorine, iodine, fluorine present. This would be considered generally an organic molecule, but it would not be considered a biomolecule. For one factor, it has chlorine, which is present, which you usually don't find in biomolecules simply because chlorine is a poison. Here is a Fischer projection of a biomolecule, in which case this is a sugar biomolecule because it has a carbonyl group and it has a alcohol that's present. I also want to point out for Fischer projections, we tend to have on the very bottom an alcohol, and it tends to be written in a condensed structure form. Now, for the biomolecules with 2 or more chirocarbons, the Fischer projection form may look something like this. Notice how it's either a carbonyl group, carbon, or alcohol and hydrogens. Notice also for the Fischer projection, it contains a condensed structure that's on the very bottom. So in this case, here we have alcohols that are present. Notice we also have hydrogens that are present. So this is kind of redundant, straightforward. I do want to point out for these biochemistry Fischer projection molecules, we always show the hydrogens that are present. So, going back to our Fischer projection, in this slide we see biomolecules with 2 chirocarbons. Again, chirocarbons we define as any carbon with 4 different groups attached. So in this case, here we have 1 and 2. So 2 chirocarbons. Now, it turns out in biochemistry, unlike organic chemistry, biomolecules, there tends to be only one type of key isomer. When it comes to enantiomers, in a living organism, they prefer only one type of enantiomer. So, when it comes to figuring out, using the Fischer projection, whether you have a D or L enantiomer, it's very easy. All you have to do is look at the carbon, which is second from the bottom, and then ask yourself, and I'll highlight this, Is it going to be on the right-hand side for the alcohol, or is it going to be on the left-hand side for the alcohol? Oops. If it's on the right-hand side, it's going to be a D. If it's on the left-hand side, such as its opposite enantiomer, then it's going to be considered L. So this is very straightforward compared to the other single chirocarbon enantiomers we talked about. So on the right for the alcohol, D. On the left, it's going to be L. Now, let's go ahead and practice a little more. Here we have a Fischer projection. Here is its mirror image. Very easy to make. Simply flip to the other side the side groups. And now you have the opposite enantiomer. We look at the carbon, which is second from the bottom. If the alcohol is on the right-hand side, then it's going to be a D. Notice its opposite enantiomer is going to be an L. So pretty straightforward. Let's go ahead and do the same thing, only now I'm going to go ahead and use a wedge dash structure. So in this case, here's my wedge dash. Carbon, carbon. CH2OH. OH, OH, hydrogen, hydrogen. So let's go ahead and draw its opposite enantiomer. Let me go ahead and start making the wedges. Wedges are always going to be horizontal. The peripheral groups that are vertical are always going to be dashes. And here is the mirror image. Notice I simply flip to the other side each of the side groups. There we go. Now, here we have on the left-hand side, we have a L. On the right-hand side, we have a D. So very straightforward. I do want to point out when we have bonds between these inner carbons, we always write them as dashes. So even though it's a wedge dash structure, we would write them as dashes. The dash would be the same thing as a, we write these center carbon-carbon bonds as single lines. Single lines. So let me repeat that one more time. We write these inner carbon-carbon bonds as single lines. And then the outside peripheral carbons we write as dashes. So let's go ahead and go straight to our handout. I want to point out to you on this one right here, on D, I would actually classify this roughly as an organic molecule, but it would not be a biomolecule. Notice it has chlorine on there. Also notice there is no carbonyl on there, so it's not a biomolecule that we've talked about, such as sugar. So if you're watching this, which you should be, you can actually ignore this particular row. So we won't be tested on this one, and you won't have to actually do this one. So less work for you to do, provided you've watched this commentary. Let's go to F right here. I'm going to go ahead and go through the boxes now that we know how to do everything. Let's go ahead and create a Fischer projection. Oops. Let's bring it up a bit. It may not fit. Oh well. So it's down here. Let's go ahead and modify this and make this a Fischer projection. There we go. Now let's go to the center. Let's go ahead and classify this. And this is going to be a aldo, 1, 2, 3, 4, 5, pentose. Is this an enantiomer? Yes, it is. Why? Because we can create a mirror image of this, and it has a chirocarbon. It has multiple chirocarbons. So all it needs is one, though, to be considered an enantiomer, or an enantiomer candidate. Bottom line is we would put yes for the answer. And finally, let's go ahead and draw the opposite enantiomer in both Fischer projection and wedge dash structure. So I'm going to go ahead and make a copy, and then I simply flip the horizontal groups from one side to another. Voila. Oops. Notice how the hydrogens are on the wrong side, so I'll go ahead and I'll adjust those as well. Now, I'm going to create a molecule which is the same one, only it's going to be in wedge dash form, and I'll make it right next to it. Now we have a sketch which is in wedge dash form. Notice these central bonds, which I'll highlight in red, are actually just single lines. So this means they're in the same plane. So this is how we would write it. For these multi-chirocarbon biomolecules, again, nothing fancy. When we start identifying whether they're D or L, all you have to do is look at the second carbon from the bottom and figure out, is the alcohol on the left-hand side or right-hand side. This one is on the left-hand side, and obviously its wedge dash form is also on the left-hand side. Its mirror image, therefore, for both of these is going to be on the right-hand side. Okay, so going back to our slides, it turns out that when you have multiple chirocarbons, you can have multiple stereoisomers that can form. Some of them may be mirror images, some of them may not be. If you have stereoisomers which are not mirror-like, then we call these diastereomers. So for example, here I have two molecules, and you'll notice how even though they have the same connections, they have different orientations, but they are not mirror-like. So notice the alcohols on this far right one are on opposite sides for the center one. So these are examples of diastereomers. The more chirocarbons you have, again, the greater number of possible stereoisomers. But in a living organism, the cell only prefers one type of enantiomer, much less one type of stereoisomer. So it's only going to prefer one, which really cuts down the amount of work, since if a body could accept multiple stereoisomers, then it would have a ton of work on its hands dealing with each one. In biochemistry land, when we name these, every single stereoisomer has its own unique name. So in this case right here, if we have two molecules which are stereoisomers of each other but they're not mirror images, then they have their own unique name. So the one on the left is called erythros, the one on the right is called threos. Each one can produce its own mirror images. There is a L erythros, there is an L threos. And again, nature only prefers one type of stereoisomer at a time. Now, one unique property about enantiomers in general is if you were to sit there and stick enantiomers in a special instrument called a polarimeter, we would notice some unique things about them. So, a polarimeter has on one end a polarized lens. So what that means is the lens has these tiny little slits, and it basically cuts the light into these single planes of light, which we call polarized light. So single planes of light. And it turns out that when they pass into a polarimeter where it contains the pure enantiomer, it will actually rotate that plane of light. It will either rotate it clockwise or it will rotate it counterclockwise. One of the two. It turns out if we have a pure enantiomer, a pure enantiomer will rotate the polarized light one direction. So D enantiomer for glyceraldehyde will rotate it clockwise, which we represent as a positive. If, on the other hand, I had the opposite L enantiomer, it would rotate it counterclockwise, which we represent as a negative. Now, polarimeter will actually measure how many degrees clockwise or counterclockwise it would rotate. So what would we do? What we would do is we would have crosshairs, and if there were no pure enantiomer present, as a plane of light hit us, again it's all in one plane, it would go up and down. However, if we were to sit there and put a pure enantiomer in there, and I'm just going to go ahead and draw a crude Fischer projection of an enantiomer. The minute the polarized light hit that enantiomer, it would go ahead and rotate it. So it would rotate it either clockwise or counterclockwise. And a polarimeter will actually measure the degrees that it would rotate it, either positive or negative. So in general, we have to do an experiment to figure out whether one pure enantiomer will rotate it clockwise, positive direction, or counterclockwise, the negative direction. We can't just assume that there is a direct relationship. We have to do the experiment. Once we figure out, for example, if D enantiomers, for example, rotates light a counterclockwise, then we can go ahead and assume that the opposite enantiomer will rotate the light the opposite direction. But there is no direct correlation between D positive L minus or D minus L positive. You have to first do the experiment first. And this instrument which performs the experiment, and this is a great bonus question if you're watching the commentary, is called a polarimeter. Polarimeter. That's the instrument name. Finally, what happens if we have a 50-50 mixture of our enantiomers? Then the enantiomers would cancel out rotation. So as one enantiomer rotated at one direction, the opposite enantiomer would rotate the polarized light the opposite direction. So they would cancel each other out. So it would, if it's a pure mixture, it would show up as 0 degrees, and it would be, the plane of light would be straight up and down, no rotation. This is called a racemic mixture. A racemic mixture. So one unique thing, or one unique difference between biomolecules versus non-biomolecules, or our traditional organic molecules. So for biomolecules, they exist only as a pure enantiomer, whereas all non-living originating molecules that are organic, but not biomolecules, so I'll just say non-biochem, they occur naturally in nature as a 50-50, aka racemic mixture, in which case you see no optical rotation, because the positive and minus, they cancel each other out. So, a lot more information than the slide currently says on there. Know these general terms: clockwise, counterclockwise, positive, negative, and of course, above all, know the instrument used to measure optical rotation is called a polarimeter. If you're watching the slide and this slide still exists on the original handout, go ahead and cross this out. In future classes, I'll actually get rid of this slide for this particular section, for the 347 section. But for right now, it's probably still in there, so cross it out. So that concludes our section of commentary for these slides.